Welcome. To any visitors, I'm Professor O'Malley and I teach engineering at Benedictine College in Atchison, Kansas. This video will walk through an example of solving a dynamics problem where the mass is not constant. To analyze the situation, we'll end up using impulse momentum methods. Recall that F equals ma is actually a simplification of Newton's second law for the special case of the constant mass system. The second law really says that the sum of all forces is equal to the time rate of change of the object's linear momentum. If you remember, linear momentum is mass times velocity. If the mass and the velocity are both changing as time goes by, in order to take the time derivative, you would normally use the product rule. But in this case, what does v mean? Remember, Newton's second law should work for any inertial, or that is non-accelerating, reference frame. But if we're measuring v relative to two different origins moving at different constant speeds, we would end up getting different answers for the term dm dt times v. So what's going on? To sort it out, let's take the example of a rocket in deep space where gravity and drag are both negligible, and we'll use the impulse momentum principle to analyze the situation. At one instant, the rocket has a mass m and is moving to the right with some velocity v. At a later instant, some mass has been exhausted out the back of the rocket. We'll call this dm. We'll treat the rocket as one particle and the exhaust gas as a second particle. The rocket now has the mass m minus dm and is moving slightly faster, so we'll call it v plus dv. The gas has the mass of dm and is moving with velocity v plus dv, which is what the rocket was, plus u, where u is the relative speed at which the exhaust is ejected from the rocket. In this case, u would be a negative number because the rocket is shooting the exhaust out the back to the left in the drawing relative to the rocket. So let's apply the impulse momentum principle. On the left side, we're integrating all the internal forces with respect to time. In this case, we'll say state 1 is at time 1 and state 2 is an instant later at t1 plus dt. On the right side, we have a net change in the linear momentum between the two states. If we do the integration on the left side, we'll just get the sum of forces times dt. On the right-hand side, for state 2, we have linear momentum terms for the rocket and the gas, and for state 1, we just have the rocket based on the diagram we drew earlier. Plugging in the terms and doing the expansion, you'll notice that a bunch of the terms will end up canceling out. And we're left with the following expression. If we divide both sides by dt, we have the sum of external forces on the entire system is equal to the mass times dv dt, which is the acceleration of the rocket, plus dm dt, which was the exhaust rate, times the relative velocity of the exhaust u. Note that the thrust force exerted on the rocket by the departing exhaust is an internal force, and it doesn't show up in the sum of forces on the left-hand side. So putting some numbers on it, if the rocket with a current mass of 10,000 kilograms, including fuel, is flying through deep space and exhausting gas at 120 kilograms per second with a relative speed of 1,000 meters per second, what is the rocket's acceleration? Adding these numbers to our original picture and plugging in the equation we derived and solving it for dv dt, you can see that the acceleration of the rocket is 12 meters per second squared. Just make sure you're being careful with negative signs as you go through the calculations until you get the hang of it. Let's change the situation slightly now and say that the same rocket were instead trying to lift off from the launch pad on Earth instead of flying through deep space. We'll need a new free body diagram where the weight of the rocket or the effect of gravity is included. Our sum of external forces is no longer 0, but is now equal to minus w. Resolving for the acceleration, we would expect it to be lower, and sure enough, we get an acceleration that is g less than our previous result, leaving us with 2.19 meters per second squared. As the liftoff progressed, drag due to air resistance would also come into play, but we'll save that for another time. Lastly, what if we wanted to figure out the thrust force exerted on the rocket by the departing exhaust? In this case, we would just draw a free body diagram of the rocket and leave the gas out. Here, the sum of forces is equal to the thrust minus the weight. That adds up to mass times acceleration. Thus, based on what we had a minute ago, the thrust force must equal negative dm dt times u. So that's how you solve non-constant mass problems in a nutshell. Thank you for watching. Hope you learned something from this video, and please feel free to leave comments or questions below.